Hello and welcome in this video. In this video, we are going to solve the question number 3 of the data science assignment 3. So let's get started. From question 3 says, explain the purpose of training, test and validation sets in machine learning. What is the cross validation and how does it differ from a simple train validation test split? Solution of this question. Training sets. This is the actual data sets from which a model trains, i.e., the model sees and learn from the data to predict the outcome or to make the right decision. Most of the training data is collected from several sources and then pre-processed and organized to provide proper performance of the model. This data is more than 60% of total data available from the project. Testing sets. This dataset is independent of the training set but has a somewhat similar type of probability distribution of the classes and is used as a benchmark to evaluate the model. Used only after the training of the model is complete. Testing set is usually a properly organized data sets having all kind of data and for the scenarios that the model would probably be facing the used in the real world. This data is approximately 20 to 25% of the total data available for the project. Validation set. The validation set is used to fine tune and hyperparameters of the model and is considered as a part of training of the model. The model only sees the data for evolution but does not learn from this data, providing an objective, unbiased evolution of the model. Validation dataset can be utilized for the regression as well by encrypting training of model when loss of validation dataset become greater than loss of training datasets, e.g. reducing bias and variance. This data approximately 10 to 15% of the total available. Cross validation in machine learning. Cross validation is a technique used to check how well machine learning model perform or unseen while the data preventing overfitting. It works by some specific function, splitting the dataset into several parts, training the data model on some parts and testing it on the remaining part. Report this resampling process multiple times by choosing different part of the dataset, averaging the result from each validating step to get the final performance. The type of cross validation. There are several type of cross validation technique which are followed. The first one is hold out validation. In hold out validation method, typically 50% of data is used for training and 50% for testing, making it simple and quick to apply. The major drawback of this method is that only 50% data is used for training. The model may miss important pattern in the other half, which leads to high bias. Second one is LOCC, leave one out cross validation. In this method, the model is trained on the entire dataset except for the one data point which is used for testing. This process is repeated for each data point in the dataset. All the data points are usually for training, resulting in the low bias. The second function is testing on a single data point can cause high variance, especially if the point is an outlier. It can be very consuming of time for the large datasets as it require one iteration per data point. The third one is k-folding cross validation. K-folding validation splits the dataset into k equal sized folds. The model is trained on k1 fold and tested on the remaining fold. This process is repeated k times each in using a different fold for testing, checking the aspect and training validation test, split and cross validation, checking some difference between them. Splitting style. The database is divided only once for example into 70% training, 15% validation and the 15% of testing. The model is trained on the training sets and tuned using the validation sets. Results depend completely on the single split. In cross validation, the data sets divide into a k equal sized fold. The model is trained k times each time using a different fold as a validation and the remaining fold as a training. Every data point get a chance to be validation exactly one. In model training count, the model is trained only one time, which makes the process computationally fast and hyperparameters are tuned based on the performance of the single validation set. Since there is only one training opportunity, the result may not represent in the true performance. The model is trained k times. Every iteration uses different training and validation combines providing multiple performance observation in the final performance matrix. The average across all folds give a reliable estimate in the cross validation. In the validation reliability, the performance highly depends on the random splits. If the validation sets happen to be the easy or difficult the model, evolution may be biased. This something leads to be overestimate or underestimate of the model capacity. In this, the general performance is averaged across the multiple validation, reducing randomness since every subset participate in the both training and validate. It's give a fair and stable estimate of generalization ability. This drastic. The suitable data size in the first work well for the large data sets, where even after splitting the training and validate data sets still contain many samples. In small data set, perform may be misleading because training data become too small. Another one, best of small and medium data sets, where using multiple folds allow maximize utilization of available data even if total data is limited. The model trains on the most of the it every time improving learning stability. Computational cost. Computational cost in first method. Very low computational cost burden since training happen once. Suitable when model training is expensive, deep and learning and models or use data sets. Ideal when speed is prioritized over evolution precision. In second method, computational expensive because the model training k time complexity grow with the higher k and complex models suitable when accuracy and reliability matters more than the training data time. Overfitting risk in both high higher because performance tuning depends on a single validation set. The model may be optimized too much for the one validation distribution and fail on complete unseen data. In second method, lower, since because the model is evaluated across the multiple validation sets, reducing dependence on the fixed distribution, it gives a more realistic view of how the model will perform in in, in this video. That's all for this video. Thank you.